So today we have our second big idea from calculus, the derivative, so I suggest paying attention. Once again, we've got your keywords up at the top there. I would look out for them. I'm going to take them off on the future slides because we need the room. But here is our big motivation for the day. Okay, so suppose we have a graph that shows my position at various stages along a trip. So horizontally here I've got time in minutes, vertically I've got how many miles I've gone, and so we can see as we move along at time 0 I haven't moved. After 10 minutes, I've moved up about, I'd say 10 miles, 20 minutes, 20 miles, and we keep going along here. So a very natural question you could ask is, well, what was my average speed during my trip here? And so what we do is we look down here at the corner, we see that, well, at time 0 I started at 0, and I ended my trip at 60 minutes up here at 60 miles. So one thing I hope you think is that this is not an area question. If I found the area underneath my curve, what I'd have is I'd have mile minutes as my units. I don't know what a mile minute is, but it's definitely not what speed is. Speed, we need to compute miles per minute instead. Okay, speed's a rate, so it's going to be a something per something. So to find my average speed, what we need to do first is we need to first figure out the distance that I traveled. And we're going to use some notation here that we're going to use several times more. And so we're going to take my change in distance, which we're going to represent by this delta y here. So we're going to take 60 miles at the end minus 0 miles at the beginning, gives me a total traveled of 60 miles. And this little delta, again, we always think of as the change in y. And the big thing to remember is that this is all one symbol all together. Okay, it's one thing. You can't cancel deltas. And so after figuring out the distance, what we need to do next is we need to divide by the total change in time. And so the change in time, this time is going to be a delta x because it's the change in my x value along the x-axis. 60 minus 0 minutes. Delta x again is a change in x. And now I'm going to divide the two quantities. And so this means that my average speed is going to be equal to the change in my distance divided by change in time, so 60 over 60, which gives me 1 mile per minute in terms of my units. Now an important thing to notice here, that really all I've really done is I've taken my starting point here, and I've taken my ending point over here, and I've calculated the slope of the line between them. Really what we're doing here is we're just trying to figure out the slope between 2 points. Now a very natural question, of course, to ask is, what if I want to know my speed at other times? So for example, during the first 30 minutes, I know I was traveling also at 1 mile per minute, and I can calculate this, and I can see that my change in distance in this case is going to be 30, and I can also see that my change in time is 30. So when I divide these two quantities, I end up again with just 1 mile per minute. So this isn't too bad. As long as this section is straight, I can figure out my slope pretty easy there. But a natural question is, well, how do I figure out the slope on the curvy part? So if I look over on my graph, on the green section of my graph here, and say I decide I want to know, well, how fast was I going when at this time 50 minutes? Well, the problem here is that my graph isn't straight anymore. It's not a straight line. So what we need to do is we need to come up with a way that makes sense out of the idea of slope along a curve and what happens there. So one last idea here. What we really are going to do here is we're going to use calculus to move from the idea of calculating our average speed over an interval, say 45 to 55 minutes on the graph, to a new idea of instantaneous speed. What we can see if we look at this curve is it's changing all the time, and that's the whole point of calculus, is to somehow grab hold of the fact that this thing's changing all the time. It's no longer a straight line. And so what we want to do is we want to figure out exactly how fast I was going at exactly 50 minutes. So we want to know exact speed at an exact time. And that's what we're going to figure out how to do in the next few minutes. And so what we plan to do is we're going to set out to solve what's called the tangent line problem. And as always, we need to introduce some notation to make our life easier. So we're going to start off by saying what we've got over here is we've got a point that we're going to call P on our graph, and it has x coordinate c, and its y coordinate is f of c. Also, we're going to pick another point on our graph, let's call it Q, and this point Q is over here at coordinates c plus the change in x, our delta x, and its y coordinate is up here at f of c plus delta x. And so what we can do is we can build the line through these points that we're going to call a secant line. And a secant line is just a fancy way to say that the line goes through 2 points on our graph. And so what's interesting is that this distance here between c and delta, c plus delta x, is delta x, and this distance vertically between p and q is delta y, but what we're going to do is we're not going to write this quite as delta y. And so what we write is we write that the slope of the secant line is going to be equal to here, this quantity, which in the numerator is just our change in y, and in the denominator ends up being our change in x. So often what we do is we just shorten this down. And so what we have is we have this quantity over here, which is the slope of our secant line. It's the change in our vertical divided by the change in our horizontal. And this quantity is also a lot of times called the difference quotient. The reason for this, of course, is because in this quantity we take the difference between some numbers, both in the numerator and the denominator, and then we take the quotient of everything. So it's just called the difference quotient. Now, of course, the problem with computing the difference quotient for the secant line is that it's just an approximation. And what we want to do is we want to get the best approximation. And so what we need to do is we need to take this point Q over here and slide it on over so that it gets closer and closer to P so that we get a better approximation for the slope. Now what this also means is we need to take this delta x and we need to make it smaller, because by moving this horizontal distance and making it smaller, that'll bring the point Q closer and closer to P. Now the issue here, of course, is that this is good for our difference quotient, it'll give us a better result, but we need to make delta x go towards 0, but we can't let delta x equal 0. We want to approximate it as we get close, not what happens at 0, because of course we don't want to divide by 0. And of course we use our good old limit again, because limits let us get close to stuff without actually figuring out what happens at the place where it equals 0. So we have our definition. If f is defined on an open interval containing a point c, and if this limit, that is that what we're going to do is we're going to compute the difference quotient, the slopes, and what we're going to do is we're going to compute more and more accurate slopes equals some number, then the line passing through this point with slope m is called the tangent line to the graph at that point. And this place is going to be called the slope at c. So just to reiterate one more time, this number m, if you can calculate this number, is going to be the slope of the tangent line, the slope of the graph at c, and we'll see in a second it's also going to be called the derivative at c as well. Lots of good words for it, all ways to calculate the slope along this curvy bit. So what we have here is we have the graph again of my original example of my distance over time. And what we're going to do is we're going to try to figure out what the slope is here at this point over here. And so to do that, first thing we want to do is we want to just zoom in a little bit. And if we zoom in a little bit to get a better sense of what we're doing here, what we can see is we've got our point over here, the purple is the P, and over here is our Q. And right now, if we calculated the slope, we'd get an approximation for the slope at the purple dot here, but it's not very good. We can see that these lines don't really meet up very well. So what we do is we take and we move that point closer, and as we move it closer, we make the distance between them smaller. That's our delta x. And as we make that distance smaller, they start to line up better and better and better. And what's going to happen actually is we can even zoom in more, and we can see that if we keep zooming in, what we can see is that this green graph that looked like a curve before starts to look like a straight line. And in fact, what happens is as we move this point closer and closer to it, they start to meet up almost perfectly. So when we pick 2 points on the line that are really, really close together, it really starts to look like a straight line, just like our graph. And when this happens, this graph is now called the tangent line. So the tangent line is the line that has the same slope as the point that we're finding the slope at. So they match up perfectly if we zoom in far enough. The big key here is that that green line really, that was a curve, really starts to look like a straight line, and the secant line really starts to approximate that line. So just to reiterate, the tangent line will be the line that has the same slope at the point, and it's given by the equation here if your point has coordinates c, f of c, where m is the slope at that point. Okay, so let's take this new definition out for a ride. Let's find the slope of the graph of the function f of x equals 4x minus 2 at the point 310, some point on the graph. So the first thing we do is we recall our definition that we need to compute a limit as delta x approaches 0 of f of c plus delta x minus f of c all over delta x. In this case, we know what our function is, and this 3 number is going to be c. So c equals 3, it's the point we're interested in. So the first thing is we put in c equals 3 into our definition. And the next thing we want to do is we want to use our particular function f of x. So here what I've done is I've taken 3 plus delta x and put it into my function. So I've replaced each x in it with 3 plus delta x. So I've got 4 times the input 3 plus delta x minus 2. And in the second one, I've put 3 into my function, so I'm going to subtract 4 times 3 minus 2. Next I want to do is I want to work towards simplifying my expression. Now, the idea here is this is going to be the same as before, is when we calculated limits. The problem is we want to figure out what happens as delta x gets close to 0, but we can't just substitute and compute because it'll divide by 0. So our goal is going to be to simplify down to hopefully we can cancel this delta x out. Now fortunately, we've simplified until lots of things cancel out. And so now what we can do is we can cancel delta x. Now important note here, you have to cancel the whole thing. You can't just cancel off a single delta or something like that. We're going to cancel off this whole delta x with this whole delta x. And sometimes this step is going to require you to factor. In this case, there's nothing to factor. It just cancels pretty nicely, but in some cases this will work. So now we take our limit and we find out that we get an answer of 4. So the question is, well, does this make sense? Does it make sense to say the slope of f of x equals 4x minus 2 at 310 is 4? Well, I hope it makes sense to you, because we just calculated the slope of a straight line, and the slope of a straight line sure is 4. Now if you want to find the slope at any point, you can go through with your definition there and work through it all the time with any particular number you want. You can try it for, instead of for 3, you could try to find the slope at 4, you could try to find the slope at 5, whatever. But what we can do is we can also do this in a way so that we'll get the slope at any point instead. So again, to find it very abstractly, we start again with just our definition of slope. And now we use our function and we substitute in our function here. And so here what we've done is we've taken x plus delta x and put it into our function. And we've also taken just x and just put it into our function. So this is just a nice substitution using our f, our function. And next, it's just like before, we're just going to try and simplify and cancel stuff down. And so what we can do is we can just write this out. So this is going to be the limit as delta x approaches 0 of 4x plus 4 times delta x minus 2 minus 4x plus 2 if we distribute our negative correctly. And then we're going to see a whole bunch of stuff cancel. So let's see, this 4x cancels with that 4x. This negative 2 cancels with the positive 2. And look what we're left with, very similar to last time. 4 times delta x over delta x. Those delta x's cancel, and so we're left with a really nice limit that again our slope is 4. Our slope is 4 everywhere. So what have we done? We've done something incredibly important. We figured out the next important super definition of calculus, and that is the derivative of a function at f is going to be given by this formula. The derivative, which we use in symbols, this little prime notation, so this is pronounced f prime of x, or the derivative of f of x, is going to be what you get when you compute this limit abstractly with x's in there. Now, one little note down here I want to add is that sometimes you'll also see this as the limit as h approaches 0 of f of x plus h minus f of x all over h. So you just replace h with delta x's. Some people like delta x, some people like h. Doesn't matter. It's the same thing. We're just letting something go to 0. So a few notes about this. This only works if you actually get a function out on the other end that makes sense. Sometimes you'll get some stuff that does not exist, so just be careful there. Next, that this is a function that takes as input x and outputs the slope of f at x. Okay? So it's very important. You give it a number, it'll tell you what the slope of the function is there. The process of finding a derivative is going to be called differentiation, and any function we can take the derivative of is going to be called differentiable. And lastly, if a function is differentiable for all x in ab, then f is going to be called differentiable on the open interval. So I know it's kind of weird here that last time we had integrals and we integrated and they're integrable, and here we have derivatives and we differentiate, we don't derivate. But I think you'll get over it. These are just the words we're going to use. So one last problem before we move on and do some more examples is that there's lots of different notations for this. Well, there's only one way to write an integral, that fancy s-looking thing. There's lots of ways to write derivatives. So some people do this. Nice prime notation here. This was invented by a mathematician named Lagrange. This one right here, this was Leibniz's favorite. He liked to use d's because he was taking the derivatives of stuff. Again, this is the mathematician Lagrange liked primes. Here, we're back to the Leibniz guy again. This last one over here, this is a mathematician called Euler. He was kind of neat. He liked d, the derivative, big D, I guess, whatever. But lastly, here's the problem. This was Newton's notation. Newton put a dot over his functions. Physicists still do this, apparently, but it's widely regarded by mathematicians as terrible, terrible style. You do not want to put dots over your functions. Please don't use this one. This one's not allowed. I'm going to cross it out. So let's do one last example here. So let's go ahead and try to find the derivative of f of x equals x squared. So in this case, what we need to do is, again, we just go back and we set up our limit definition. So we're going to take the limit as h approaches 0 of f of x plus h minus f of x all over h. So it's the same thing as before. H is just representing this something that we're going to make small. And so this is going to be the limit still as h approaches 0 all over h of now x plus h squared minus x squared. So this becomes the limit as h approaches 0, and now we FOIL, or whatever you want to call it, distribute x squared plus 2xh plus h squared minus x squared all over h. We go ahead and we go through our canceling step, the limit as h approaches 0. Oh, nice. These x squareds cancel, so that's good. So we're left with 2xh plus h squared all over h. Now here's a step that students sometimes struggle with. In order to cancel an h, we have to factor, okay? So this requires a bit of factoring here. And so what we're going to do is we're going to factor in h out of the numerator to leave with 2x plus h all over h. And now these h's, they cancel. And so we're left with the limit as h approaches 0 of 2x plus h, which now we can just directly substitute, and we're going to get 2x plus 0, so 2x. So this means our derivative of our function is the function 2x. This is the function that you give it a point, and it's going to tell you the slope of x squared. So let's take a look at this graphically. So what we have here is we have the graph of x squared given in red, and we just figured out that its derivative is going to be 2x. And we want to think, well, does this make sense? Does this really capture the idea of slope of a function? So let's make a table and see if this makes sense. So the first thing we want to check is we want to check everyone's favorite point. Well, if x is 0, what is f prime of x? Well, this is going to be 2 times 0, so it's going to be 0. So we want to think on our graph, does it make sense that at 0 is the slope equal to 0 there? It kind of does make sense. It looks as if the slope is kind of going downwards and then it reverses direction. So around here it looks like it kind of makes sense to say that the slope is 0. Well, let's see our next favorite point, 1. Well, if we take f prime of 1, we're going to get 2 times 1 equals 2. So does it make sense to say that the graph here has a slope of 2 right here? Well, if we sort of approximate the slope there, what we can see is that looks like about 2. It looks like we did a run of 1, a rise of about 2 units there in that nice triangle. And so it makes sense to sort of say that at the point 1, our slope is 2. So we'll make a nice little dot there. Well, at our third favorite point, negative 1, the derivative we just calculated says that our slope is going to be 2 times negative 1 is negative 2. So again, we ask the question, well, does this make sense? If I go to my graph at negative 1, and I look there, and I try to draw myself the slope there, well, what looks like it happens there? Well, it's definitely negative. We're going down. And again, it looks like a slope of about negative 2. Our rise is negative 2. We're going down. Our run is still 1. So it makes sense to say that our slope there is going to be negative 2. And what you can do is you can do this for all different points in between. You can sort of estimate what you think the slope will be at any given point and connect them all together. And so in this case, this actually looks good. This is the line y equals 2x, and it seems to be always capturing the idea of what the slope is of the red graph. So this can be a little tough and it's a little confusing. So next what we're going to do is we're going to look at a computer application where you can practice this. So we're going to use this app in order to practice sketching the graph of a derivative. So what we have in this top box is we have the graph of a function, and our goal is to sketch the graph of the derivative, that is all the slopes along it, in the bottom graph here. And the first thing we want to do is we want to make sure we hit this auto button over here because that's going to help us sketch our graph. So if we look along this graph, some places are pretty easy. It's easy to see that we have positive slope here from about negative 1 to 0. We have negative slope here from 0 all the way over to 1 3/4. 0 slope again, positive, negative. And we want to record that below, but we want to be more precise. So if we look over here, if we look at this stretch right here, it looks like it's about a rise of 1 unit and a run of just half a unit. So that means we have a slope of about 2 over here. So what we're going to do is we'll click on this line and drag it up, and we'll drag it up and bring it up over to around 2. And then what we can see is we're sort of leveling off until we get near here where our graph has a slope of 0 again. So we can just kind of click and drag and hold this and kind of smooth it out a little bit here. And then here we have to start being negative. And as we move over in our graph, well, in this region here, it looks like we're doing a rise, I would say, of about negative 1 over a run of about, I would also say again, maybe just in this case, though, it's only a run of 1 unit, or 1/2 unit. So this means we're going to have a slope of about negative 2 here. And as we move over, you can see our slope gets pretty steep over here. I would say around here, if we measured carefully, we get a slope of negative 3. But then we're going to start coming back down. We've got to go pretty quick because we've got to get back to a 0 slope here. And now we're going to have positive slope. And again, if we measure carefully here, and we look, I would estimate this slope to be about, I'd say around 4/3, maybe a little higher than that. But then we got to start going back down in our slope again because our slope has to get back to 0. I'm just going to smooth this out a little more. We got a slope of 0, and then we got a nice negative slope again here. And so once you think you've got a pretty good looking graph, you want to make sure it's really nice looking, okay? I'm going to warn you about this. Take your time with this thing, because what you're going to do is you're going to go over here and click check your answer. And once you check your answer, boom, it's going to give you this picture. Yours are the dotted green lines. The solid green line behind it is the actual calculated slope. and it can kind of show you visually, where you were really close, where you were a bit far off there, and it's going to give you a score over here. Now the important part is your score needs to be at least 80% in order to pass. This is a pass, no pass situation. If your score is above 80%, then take a picture of this with your phone and email it to me, or try to take a picture in some other way and let me know what you got. Someone has a phone that takes pictures and can send it to me. Whoever gets the highest score in the class gets a bonus point on the next exam. Now, suppose you click this button and you didn't get 86%. Well, what you can do, you can't go back and try to fix this one. You're done. What you got to do is you got to click a new function, and you got to start over from scratch. So it didn't take me that long to draw mine, but if you're not very good at this, you're gonna have to be clicking new function quite a bit, and you're gonna have to just keep clicking. Okay, keep clicking new function. Try to keep clicking until you get one that looks pretty easy though, and well, good luck. But this is due tomorrow. But remember, top score gets a bonus. The link to this app is available on the Blackboard website right beneath the video. If you have any troubles with it, let me know. It does require Flash, so you may need to use a different computer.